Yeah, we can.
Cool. So thanks for having me. So I'm actually Josh Violin, the ad software right here. But so today I'm very glad to talk about our work, strong gravitational lensing parameter estimation with vision transformer. And this is a joint work with Guangwei, Jeff, Bowen, Shenjie, Jiarong, Vishal, and myself. So to begin with, I'm going to switch gear a little bit because I'm a former astrophysicist, so I work a lot on cosmology. So one of the key questions we're trying to ask about is that how can machine learning help us learn about things about like our universe? And one of the key questions that we're thinking about today, in particular for this presentation, is that we noticed that the universe is expanding, and there are multiple ways of measure how fast our universe are expanding, called the Hubble constant. And recently, there has been some attention in different methods of estimating the Hubble parameters. It turns out that strong gravitational lensing, which is like, in some sense, if you have a distant quasar, which is a supermassive black hole, and you have some foreground mass, foreground galaxies, you could actually ray trace the light from the distant quasars, and they will form into like these super beautiful Einstein ring and Einstein cross, as you see right here. So on the top, as you can see, there are four multiple images coming from the same black hole through this gravitational lensing effect. And they're actually pretty good ways of probing the Hubble parameters. And so the next question we have is that traditionally we noticed that it's actually pretty hard to model these strong gravitational lensing. One of the challenge is that we actually, when we look at the image, we don't actually know what the source, what the background is, and what the foreground mass distribution is, because most of them are dark matter dominated. So it usually takes weeks or even months or even a PhD student's life to model just one single strong lensing images. And in the near future, we're going to have like hundreds of thousands of these strong lensing with a new survey. So we've been thinking about ways to speed up the analysis pipeline. So in recent years, machine learning, and in particular convolutional neural network, has shown really promising results on strong lensing modeling. For example, like parameter estimations and using Bayesian neural network for Hubble parameter estimation as well as uncertainty estimations. And however, recently there's a new type of computer vision tools called vision transformer, which is really popular in the last few years. So one of the things we've been thinking about is that what can vision transformer help us on this kind of problems? And in case some of you are not familiar with it, this is the original paper. It's called image is worth 16 by 16 words. So our idea is that instead of using convolutional kernel, we take patches of the from the image and use something we call the self-attention mechanism, which due to time I'm not going to explain too much about it, to basically do the same computer vision task. And the good thing about these vision transformer is that because now we are using self-attention mechanisms, so there might be some chance that you can capture the long-range interactions from the same images, which is very different from how a convolutional neural network usually operates. And in our case, we thought that that might be a really good tool for strong gravitational lensing. So that's exactly what we do, an experiment. And because of we don't actually have so many real physical data with a really good labeling at this moment, so we use simulation to help us build some of these strong gravitational lensing images as a training and testing and validation sets. So as you can see right here, we use the lens rounding pipeline. So there are basically you can see in each lensing image there are some background lens quasar, foreground lens galaxies, and going on right here. So what we did is that we did something really straightforward. Is that we took a vision transformer and a ResNet and basically modify them so to do a regression test using different kind of losses, including MSE loss and a negative likelihood loss, which include uncertainty with a dropout. So in our result, we actually saw that vision transformer actually works pretty well in a lot of ways. It's comparable with ResNet. And in most of the cases, actually, it outperformed ResNet on the 7 of parameters we are interested in modeling right here. So we found that vision transformer is actually pretty cool tool for doing such a job. And we are also pretty curious about like what the transformer actually learns. So we look at different attention head to look for interpretabilities. So actually, when we look at different attention head, we notice that in attention head 2, they tend to look at the quasar, and attention head 1 and 4, they tend to look at the background lens galaxy. So we thought that's pretty cool. So in conclusion, we found that vision transformer can reach comparable results, and we think that it could be helpful for strong lensing science because with more suitable inductive bias that tackles long-ranging informations. And different attention heads seems to be dealing with different parts of the lens, so we felt that that's pretty interesting. So if you're like our work, here's our open source code and the paper link to the archive. Thank you so much.
All right, thank you.